This ShowMe is about scientific notation. When we represent a decimal number in scientific notation, we write it as a times 10 to the n. You'll notice that this is one of the last applications of a deprecated symbol for multiplication. We generally don't use x for multiplication anymore. As we move into algebra and in more advanced kinds of mathematics, x is more commonly a variable, so seeing it used this way can be confusing. However, when you go into scientific applications, particularly in physics, astronomy, and chemistry, and in certain aspects of biology that intersect with those, you end up working with very large and very small numbers. And those numbers are very inconvenient to write in their totality. We'll take a look at that here in a minute. Scientific notation makes it possible to appreciate the magnitude and meaning of the number without having to write out all of its digits, which is sometimes a really tedious task. So we're going to focus on how to use scientific notation to represent very large and very small numbers. And we're also going to take a look at using it to compare numbers and go over at least one example of multiplication. Note that in scientific notation, the number a has to be at least 1, but it has to be less than 10. The effect of this is that when you see that part of a number in scientific notation, there's only one number to the left of the decimal point at all times. If you see two numbers to the left of the decimal point, or if you see a 0 to the left of the decimal point, then the number is not in scientific notation yet, and one of your tasks at that point might be to put the number into scientific notation, and we'll talk a little bit about how to do that. Notice the exponent n is an integer. That means it can be -1, -2, -3, and in fact it is negative when the number we're talking about is quite small. If the number is a very typical number, 1, 2, 3, 4, 5, all the way up to 10, n will be 0. And then as you get to larger numbers, the exponent n will take on more and more positive numbers. Again, scientific notation is most useful when the numbers we're dealing with are extremely small or extremely big, because it takes a lot of digits to represent either kind of number in base 10. Let's start with a really large but also really familiar number, the official national debt of the United States of America. Right now it stands at $15.4 trillion, or $15,400 billion. I got that number from the website at the bottom. It's a simulation of the changing numbers related to the United States financial situation. It gives a pretty good picture of what's going on numerically. Anyway, what we want to do is take this number and rewrite it in scientific notation. Take a look at the amount of space and work saved. Well, in scientific notation, we know that it has to be a times 10 to the nth power. We know that a has to be a number that's at least 1, but less than 10. The important digits in creating the part of the number that we're going to call a are these three digits, 1, 5, and 4. And to organize those into a number that is at least 1, but less than 10, is to rewrite them as 1.54. So the decimal point is going to go right here. That's important to remember when we think about what the value of n should be. Now, n's a power of 10, that if we actually took 1.54 and multiplied it by that power of 10, we would get the number we started with. Well, let's look at the place values and the exponents that go with them. The ones place corresponds to a power of 0. The tens place to a power of 1, and the hundreds place to a power of 2. The thousands place to a power of 3. At this point, you realize after each comma, we're going to be at a power that's 3 larger than what it was before. So after the second comma, the millions place represents the 6th power of 10. The billions place represents the 9th power of 10. And the trillions place represents the 12th power of 10. But to accomplish our goal, we have to take the decimal point from a position just to the right of 10 to the 0 and move it to a position just to the right of the 1. The 1 is in the position that corresponds to the power 10 to the 13th. So, n is 13. So the actual scientific notation representation of our national debt, approximately, is 1.54 times 10 to the 13th. And that's visibly a lot shorter and a lot simpler to appreciate than the entire number that we had written out at the beginning. So that's an example of how you take a very large number and rewrite it in a shorter form using scientific notation. I do sincerely wish I could show some balance and let us work with a number that's very small related to the United States financial situation. Unfortunately, I don't think there is such a number. So we'll have to make do with a contrived small number. The number in front of us can be written in scientific notation in a somewhat simpler form. The process is similar, but of course the exponents are going to be negative because this number is less than 1. It's very small. Well, part A, that first number, has to be, again, at least 1, but less than 10. The way to organize 9 and 2 to accomplish that is to rewrite them as 9.2. That number is at least 1, but less than 10. But what power of 10 should we choose to multiply by? Well, with the decimal point where it starts, it's just to the right of the position related to 10 to the 0. Moving it to the right, we move it over 1, 2, 3, 4 places to move it to the position that it now occupies between the 9 and the 2. Well, moving to the right, making a very small number bigger each time. As we make the number bigger, our power should get smaller. How do powers get smaller? Well, when you're starting at the 0 power, they get smaller by becoming negative. And in fact, the exponent goes down by 1 with each place that we have to move the decimal point. So we moved it to the right 4 places. N is negative 4. So 9.2 times 10 to the negative 4 is another way to write the very small number that we began with. Let's take just a moment to recognize why we don't bother with this when we're dealing with numbers that are quite common. This number is my age. Also happens to be the answer to the ultimate question of life, the universe, and everything. Anyway, this number written in scientific notation is actually more work than just to write the number itself. Remember that in scientific notation, we have a times 10 to the nth. We have to transform 42 so that it's at least 1, but less than 10. The way to do that is to rewrite it as 4.2. To do that, we had to move the decimal point from its original location, just to the right of the 2, to a position just between 4 and 2. That's a change of exactly 1 place. It took a large number and made it smaller. Therefore, our power should be getting bigger to compensate for that. Well, when the power goes from 0 and moves 1 place in such a way that it makes a number smaller, that's 1 position. It's 4.2 times 10 to the first. Obviously, 42 is a much quicker and still a very easily comprehended version of the number. So this is why we don't do this with our average, ordinary, everyday numbers. It just isn't worth the effort we're putting into it. In the years to come, you're going to spend a fair amount of time with this particular number. It's called Avogadro's number. It's a very important number in chemistry. It describes the number of atoms or molecules in a proportional unit of a particular substance in a chemical equation. A very important idea. It also gives you a really good idea of just how small atoms and molecules are, because this is a ridiculously large number. To show you just how ridiculously large it is, we're going to rewrite this number in standard notation. We're only going to do this once because it also is not worth the effort, but it does help you see why scientific notation is so useful. So, Avogadro's number is going to have the digits 6, 0, 2, 2, 1, 4, 1, 5. Now, if the decimal point were to the right of that 5, we would have moved it 7 places already. When we multiply by 10 to the 26th power, we move the decimal point 26 places to the right. Well, as written, we've already done 7. We still have to move it 19 more places to the right. And that means we're going to have to put 19 zeros after the 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I apologize for subjecting you to that, but it makes the point quite clear visually about why we like scientific notation so much. If we had to name this number some other way than using scientific notation, it would be, well, ridiculously large, as I said. 602 septillion, 214 sextillion, 150 quintillion, and of course, that's approximate. A ridiculously large number, a number you could not afford to write or print over and over again in a publication. And that's why we use scientific notation, obviously a better choice. Here's another number that's far more conveniently written in scientific notation. It's called Planck's constant. It's the amount of energy in a single unit of energy. All amounts of energy are delivered in multiples of this number. Obviously, it's quite small, but it's an amazing thing that there is no such thing as an amount of energy that exists between integral multiples of this number. That's for another time, of course. The challenge here is to write this number, as before, in standard notation, and thus gain a better appreciation, literally, of scientific notation, and appreciation, especially a gratitude for it. So, here we go. Obviously, the digits 6, 6, 2, 6, 0, 6, and 8 are going to be in the number. If the decimal point is between the 6's, we need to move it to the left 34 places. That means that there should be 33 zeros before the first 6. Here we go. You can sense the frustration as my zeros tend to look like 6's and just have to write so many of them. But all of those are supposed to be zeros. Clearly, it would be a real hassle to have to write this number over and over again in a scholarly paper or publication. So we don't. We use scientific notation. A far more effective way of demonstrating that the number is very, very small, as you can tell by the extremely negative exponent, but also a way of conveying the important numbers if you're actually going to do a calculation involving this number. So once again, scientific notation, a very welcome improvement on a bad situation. Here's an example of how to use scientific notation to execute a comparison between two numbers. First, we need to have both numbers in scientific notation. Let's quickly convert the number on the left to scientific notation. As before, it has to be written as a times 10 to the nth, where a is at least 1, but less than 10. Well, the way to do that is to put a decimal point between 4 and 7. So we rewrite this number, 4.7503 times 10 to a power. Now, in putting the decimal point between the 4 and the 7, we move the decimal point 3, 6, 8 places, so it should be 10 to the 8th power. We're now going to compare that to 4.8 times 10 to the 7th. When you compare numbers in scientific notation, the first thing you must look at is the exponent. Regardless of what the numbers look like to the left, if one exponent is larger than the other, then that number is greater. Well, the exponent for the number we just wrote in scientific notation is definitely greater than 7. So the comparison is over. Now, if those two exponents happen to be the same, then you turn to the digits and compare them as though they were both numbers, again, greater than or equal to 1, but less than 10. So that's how you compare numbers in scientific notation. The first task, of course, is to put them in scientific notation, and after that to compare first their exponents and then the digits that remain. The last task I'm going to demonstrate in this ShowMe is how to multiply a number by another number in scientific notation. To start with, multiply the two numbers that are not involved in the power. So we'll take 22 and multiply it by 6.7. 7 times 22 is 154. 6 times 22 is 132. Don't forget to put your 10 in, of course. 4 and 0 are 4, 5 and 2 are 7, 1 and 3 are 4, and then we have 1. In the original set of factors, there was one digit to the right of the decimal point, so in our product there is one digit to the right of the decimal point. We can now rewrite this number as 147.4, and of course we never did do anything with 10 to the 27th, so it's still there. If this number is in scientific notation, you're done. Unfortunately, it's not in scientific notation. The value we have for A is too big. It's supposed to be at least 1, but less than 10. It's obviously too large, so we're going to have to fix that. The way to fix it is to move the decimal point so that it's between 1 and 4. So we should not have 147.4, we should have 1.474. What did we do when we did that? Well, we made the number A 100 times smaller. To balance that, then, we have to make the power of 10 100 times bigger. Well, 100 is actually 10 squared. When you multiply powers of the same base, you add the exponents. So, 10 to the 27th multiplied by 10 squared is 10 to the 29th. Now, we have a result that is in scientific notation, and the process of multiplying by a number in scientific notation is complete. If you start with either number in scientific notation, unless you end up with a very run-of-the-mill commonplace number like my age, 42, you should give an answer that is also in scientific notation. Well, that concludes our Show Me About Scientific Notation. It's kind of a hodgepodge of different things that you'll do with these numbers. But it's extremely important to master the basic skills because numbers written in this fashion are commonplace in important science classes that not only do I hope you'll take, but I hope you'll enjoy and master. They're important steps along the way to becoming a competent leader in the making of things and in the conduct of research and inquiry into the world around you. So that concludes it. You can read more about these sorts of things and ask me questions and ask me for homework help at my blog at MikePoliquin.com.